Hi, this is Mrs. Cribb, and this is your instruction video for Chapter 2B. So if you have not done so already, go ahead and pull out your notes and get to this section in your notes. We're going to be going back and forth between the paper notes and the Prezi. So here we are at the Prezi, and we're at Chapter 2B. Let me make it full screen. What is energy? Energy is the ability to do work, and it's related to the force that matter generates and the resulting action. So it's an ability to do work. In a similar way, if you have money in your wallet, that gives you the ability to buy something. So wealth, or having money, is the ability to buy something, and whatever you buy should be equal to the amount of money you spend. The value of it should be. Work involves moving something a certain distance, and so if you push really hard and you don't go anywhere, you really haven't done any work. Forms of energy are mechanical energy, which is possessed by objects that are moving, so moving energy or kinetic energy. And you could also have potential energy. So mechanical energy involves either kinetic energy of moving something or potential energy, where you have the potential for it to fall or move. Thermal energy is heat energy. Remember that therm means heat, so like your thermometer measures temperature, your thermostat adjusts the heat in your house. So thermal energy is heat energy. Then we have sound energy or acoustic energy, which when particles are moving in periodic waves going back and forth. I always like to think about a guitar string, plucking the guitar string, moving back and forth, as that's acoustic energy. Electrical energy, when you move electrons or charged particles. Wind energy from the wind blowing. Electromagnetic energy from the sun. Nuclear energy comes from the nucleus of an atom, so nuclear nucleus. Chemical energy is stored in chemical bonds, like inside of our food or just inside almost everything. Chemical reactions can either release or absorb energy. So if you have chemical energy where they absorb energy, that would be endothermic, and it releases exothermic. Now look at these words. Exothermic, exo, exiting, therm. What's therm? Heat, like in thermometers or thermostats. So exiting heat. So when heat leaves, whatever's happening, that's a exothermic reaction. It will feel warm to your hand. When it leaves, you could feel the heat coming to touch you. So hand warmers are an example of exothermic reactions. And then endothermic, the heat coming into a system. That means it's being sucked out of the environment. So if you touch it, it's going to feel cold because it's sucking the heat right out of you into the reaction vessel. We'll talk a lot more about endothermic and exothermic reactions in later chapters, but this is just an introduction to the types of energy. Now remember, mechanical is movement, so either moving now or the potential to move, kinetic or potential. Thermal energy is heat. Sound energy or acoustic energy, think about an acoustic guitar plucking the strings. Particles are going back and forth, just like those streams are moving back and forth. Electrical energy is moving charges, like electrons. Wind energy, just from the wind itself moving. Electromagnetic energy comes from the sun. Nuclear energy in the nucleus. Chemical energy, stored energy in chemical bonds. And you have two types of chemical energy. Exothermic, when the heat is exiting, leaving it, so it feels hot to you because it's coming out of something, like in hand warmers. And endothermic, where the heat is going in, so it's sucking the heat from other things, and so that makes you feel cold because it's taking the heat from your body. So that's those two slides, and this big old slide here just shows you all the forms of energy. Now, some, like wind energy, you'll notice is not listed here. So it just some of the textbooks list it and some don't. So here we go, just to help you see the leaping frog has movement energy, and an automobile has movement energy. I could say holding a rock or jumping up, standing on top of a somewhere, and you're going to jump off, you would have potential energy because you would have the potential to fall down, jump off. Thermal energy in ice cream and heating soup. Electromagnetic energy from all these resources, visible light, infrared, radio waves. Electrical energy, chemical energy, and I think we already mentioned nuclear energy as well. All right, conservation of energy. Energy being transferred and converted continuously. So energy is always being changed. If you eat something, it's being changed and those particles in the food is being broken down, turning to ATP to give energy to your cells. And your cells may cause your body to move. I mean, the energy moving around, electro pulses are moving around, causing you to move. So all of these different things are just related. Thermodynamics, so there's that therm again. What's therm mean? Heat. So thermodynamics is the flow of energy, the flow of heat, the movement and the conversion of energy. So something that's dynamic is changing. So like if you have if something is stagnant, it doesn't change at all. Dynamic is changing and more interesting in some ways. So thermodynamics is the change in the heat. So how the energy is flowing, the movement and conversion of energy. The law of energy conservation is also called the law of conservation of mass energy, or the first law of thermodynamics. Now notice how these guys are all related. Law of energy conservation is also the law of conservation of mass energy, or the first law of thermodynamics. It's probably the most important one to know, but they are all really kind of synonyms of each other. Thermodynamics, yeah, there's that term again, the first law of thermodynamics. Matter and energy can neither be created nor destroyed, only changed from one form to another. Now notice there's two parts of this definition. You cannot, matter and energy can neither be created nor destroyed. So I'm neither creating matter and energy or destroying it. I'm only changing it from one form to another. So matter can actually be changed into energy, and energy can be changed into matter, and it goes back and forth. And it comes from this formula E equals mc squared from Mr. Einstein. Okay, now we're going to watch a little video in just a second. It says, think about the worldview represented in this video. It is a godless worldview. Remember, you can still learn something from it. So that's what I really want you to get, is watching videos with discernment. We're going to learn what's valuable in this video and ignore what's not. Okay?
Where does all this stuff come from? This rock, that cow, your heart. Not the things themselves, mind you, but what they're made of, the atoms that are the fabric of all things. To answer that question, we look to the law of conservation of mass. This law says, take an isolated system, defined by a boundary that matter and energy cannot cross. Inside this system, mass, aka matter and energy, can neither be created nor destroyed. The universe, to the best of our knowledge, is an isolated system. But before we get to that, let's look at a much smaller and simpler one. Here we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. With a little energy, our molecules can really get moving. These atoms can bond together to form familiar molecules. Here's water, and here's carbon dioxide. We can't create or destroy mass. We're stuck with what we've got. So what can we do? They have a mind of their own. Let's see. They've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar and some oxygen gas. Our atoms are all accounted for, 6 carbon, 12 hydrogen, and 18 oxygen. The energy we apply is now stored in the bonds between atoms. We can re-release that energy by breaking that sugar back into water and carbon dioxide, and still, same atoms. Let's put a few of our atoms aside and try something a little more explosive. This here is methane, most commonly associated with cow flatulence, but also used for rocket fuel. If we add some oxygen and a little bit of energy, like you might get from a lit match, it combusts into carbon dioxide, water, and even more energy. Notice, our methane started with 4 hydrogen, and at the end, we still have 4 hydrogen, captured in 2 water molecules. For a grand finale, here's propane, another combustible gas. We add oxygen, light it up, and boom, more water and carbon dioxide. This time we get 3 CO2s, because the propane molecule started with 3 carbon atoms, and they have nowhere else to go. There are many other reactions we can model with this small set of atoms, and the law of conservation of mass always holds true. Whatever matter and energy go into a chemical reaction are present and accounted for when it's complete. So if mass can't be created or destroyed, where did these atoms come from in the first place? Let's turn back the clock and see. Further, 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 too far. Okay, there it is. The Big Bang. Our hydrogen formed.
All right, now you see where we're starting to go off the deep end here? We did something that's very sound and testable. We took methane and oxygen and we added heat and we created a reaction that we can duplicate. And they want to know where all these things come from, and now they're going back to something they cannot test. So this is where we have to look at our worldview. So we're not going to continue with this video at this point because the rest of it goes off into evolutionary theory, but we're going to move on. All right, the second law of thermodynamics. So the first was matter and energy, or mass, can neither be created nor destroyed, only changed from one form to the other. Remember the second part of that definition. But now we're into the second law of thermodynamics. During energy transformations, when we're changing it, some energy changes to an unusable form. Unusable. We go from order to disorder, just like my current living room or your bedroom if you don't spend time working on it. It goes from order to disorder. That's increasing entropy. We're making it messy. Entropy is the measure of disorder or randomness in a system, a portion of the universe under study. So remember, a system is just something you're looking at. Entropy increases over time. If I don't do anything to change it, entropy increases over time. Your room, popcorn without a lid, students left unattended in a classroom, all these things would increase disorder. And so here's a picture we'll go over in a second. Diffusion uses this kind of thing, evenly spreading out particles over time through motion. An example, a drop of food color in a beaker. If you took a beaker and you put food color in it, over time that food coloring would spread out evenly. You go from a high concentration area to a lower concentration area. Also, there's other things that would diffuse. So that's going from high concentration to low concentration. Now, let's move on. Here's a picture. So this is diffusion as well. We have a concentrated area. See those? All those little atoms sitting here, those molecules. This is concentrated, and it's definitely not concentrated over here because there's nothing there. And over time, they're going to spread out evenly to fill the space. The gas is spreading out to fill the space through diffusion. And then here we show an example of entropy. This is nice orderly bricks, but the entropy will increase when the bricks become disorderly. It's more probable to go from this to this without much help. To go from the disorder to order, we'd have to put energy into that system. We'd have to actually pick them up and stack them up neatly. So that's putting energy in. So entropy always goes up. I mean, that's the natural state of things. Let's watch this.
In this lesson, we are going to learn about diffusion of gases. This will help you to understand how gases behave and also explain why smells spread. Before we start, you need to recall what solids, liquids and gases are like in terms of their particles. In particular, I'd like you to ask yourself, how are the particles arranged in a gas? Pause the video and restart it when you think you have the answer. The answer is that particles in a gas are spaced out and move about very quickly in random directions. Did you get it right? This, of course, explains why a gas takes the shape of its container. It's because the particles will each continue to travel in a straight line until they hit something, in this case the wall of the container. So, the smelly gases given off by rotting vegetables in a sealed box will fill.
Now, just to throw this in there, rotting vegetables, is that a physical or a chemical change? Well, they're undergoing a chemical change. They're rotting, they're turning into something else, and they're giving off a new odor that used to not be there, and this is a stinky odor. So let's keep on now.
The box with rotting vegetables smell, but you won't be able to smell them outside the box. However, take the lid off the box and those particles will no longer bounce off the lid and be contained. They will start to escape into the air around the box. You'll soon notice the effect and will be able to smell the rotting vegetables. And that's those gas particles reaching your nose by diffusion. Diffusion is the random movement of one gas through another, from a region of high concentration, in this case inside the box, to a region of low concentration, in this case outside the box. It is a process that doesn't rely on wind or air currents. It will happen even if you are inside a building and the air is completely still. Now, there are many examples of diffusion, but smell is probably the most obvious one. These could be food smells, body smells from other people, the scent that a plant gives off to attract pollinating insects. And the same even applies with the smoke from a candle after it has been extinguished. It spreads out, and it's all due to diffusion.
Okay, now we're going to move on from there. Now we're on to thermal energy, temperature, and heat. Kinetic energy, remember, is that energy of motion. Particles are constantly moving. Even solids are constantly moving. And kinetic energy depends on both the mass of the object and the velocity. So this is the formula. Kinetic energy is 1/2 mv squared. You should have seen this in the past. We're not actually going to need to use this, but this is just to remind you about that formula. The total energy of a system is your kinetic energy, your movement energy, and your potential energy, or the energy of your position. So the temperature, now this is part that's important, is the average kinetic energy. Temperature is an average of the kinetic energy of the particles. So it's not related to the number of particles, but how much the average is per particle. Okay, per particle. Thermal energy, heat energy again, is the sum. So temperature is an average, but thermal energy is the sum of the kinetic energy. It is related to the number of particles. The more particles you have, the more heat you have. And energy always flows from hot things to cold. So to cool something down, it has to send its energy to something else, to a cooler object. And we're going to do a demonstration when we're together about the difference between thermal energy and temperature. But remember, thermal energy deals with a sum, and so the more particles you have, the more thermal energy you have. Kinetic energy deals with temperature, or temperature deals with kinetic energy, the average kinetic energy. Now, the movement of thermal energy or heat between two objects is called heat transfer, which is kind of like obvious. If I move something, I could say I transferred to another school if I moved to another school. So heat transfer is just moving the heat to another place. Remember, hot to cold. Heat goes from hot to cold. The amount of heat transferred is determined by the temperature difference. So if we have a big difference in temperature, a lot of heat moves. You have a small temperature difference, a little bit of heat moves. It also depends on how big the object is as the mass of the hotter object. So we're going to do this demo, temperature versus heat, when we're together. Here's another reminder. The warmer object will send its heat or transfer its heat to the cooler object. So see how the warmer object's temperature is higher than the cooler object? It'll keep doing that until they both have the same temperature. And then you'll see no real heat transfer at that point. Now, measuring temperature and thermal energy, we're going to be looking at joules, which is the SI unit for energy, the most important one. BTUs are the British thermal unit. We're not using that at all. I'm just letting you know there is one. Calories, this is important. Lower C calorie, lower C, is the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. So I have 1 gram of water. By the way, 1 gram of water is about the mass of a paper clip. So hold up a tiny little paper clip, feel that. That's 1 gram. And how much heat it takes to increase the temperature of that thing by 1 degree Celsius, that would be a calorie. Okay? The amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. 1 calorie is equal to 4.184 joules. The joules are the important ones. This temperature relationship, energy relationship between these two units is very important. You'll need them for some of your work. So 1 calorie is equal to 4.184 joules. So if we have to convert it, we need to use this relationship. A kilocalorie, now remember kilo means 1,000. So just like a kilometer or a kilometer means 1,000 meters, a kilocalorie means 1,000 calories. The other thing I want you to see here is that a kilocalorie has a capital C. a little calorie has a lowercase c. So a kilocalorie is what you see on your food labels. So if I have a candy bar and it says 200 calories, it's really 200,000 calories because it's 200 kilocalories in that food, which makes it sound a whole lot worse. Maybe if they wrote 200,000 calories on there, we would eat less of it. But a little c calorie is a chemistry calorie. It's what we are used to using, we use more often rather. A kilocalorie is a food calorie pretty much. It's 1,000 calories. Capital C or little c, very important. Okay, temperature scales, the Celsius scale we'll be using in science all the time. The freezing point of water is 0 and boiling point is 100. You should have been familiar with this already. Kelvin scale is the freezing point is 273 or 273.15 and the boiling point is 373 or 373.15. One thing you'll notice is there's 100 degrees between both of these. 0 and 100, that's 100 degrees. 273, 373, it's also 100 degrees. That means that these two scales, Celsius and Kelvin, have the same space between each one of their little lines on their measuring devices. Kelvin, this scale incorporates the idea of absolute zero. That's the point where no motion would happen. All the atoms would quit moving. It's a theoretical point because they've never gotten there. They've gotten close, something they created called the Bose-Einstein condensate, but we've never gotten all the way to zero, and we can't, because how do things cool off? Well, we just said that in the previous slide. See if I can get back to it. How do you cool something off? To cool something off, or to cool something down, it has to send its heat to something colder. So if I want to get down to 0 degrees Kelvin, I have to send my heat to something even less than that. Well, that's not possible. So 0 degrees Kelvin is just a theoretical point. We can get close, but we can never get there. And the other thing important about kelvins is they are never negative. If I can't get to 0, I can't get below 0. So it's never negative. And so we're going to use kelvins a lot because when we're dividing by temperature, we want to divide by something that doesn't have a negative number or doesn't have 0, really doesn't have 0. Because you can't divide by 0, can you? All right, let's look at these right here. So the first one is a Fahrenheit scale. Now notice how the markings on the Fahrenheit scale are closer together. The second one is Celsius and the third one is Kelvin. Notice how their markings are exactly the same distance apart. Okay? I don't know why they didn't line these up just perfectly, but the Kelvin scale and the Celsius scale have the same distance between their markings. Okay? So important things, 32 degrees Celsius is 32 degrees Fahrenheit is a freezing point in Fahrenheit. 0 for Celsius, 273.15 for Kelvin. And you add 100 degrees, 100 for Celsius, 373.15 for Kelvin, and 212 for Fahrenheit. Now, we're not going to be using Fahrenheit. Well, we may take Fahrenheit and convert it into Celsius, but we're not going to use it beyond converting it into another temperature. Now, temperature conversion. So these are going to be very important. Here, the formulas you're going to use. I will give you these formulas on a reference sheet. You'll get to keep that reference sheet with you. Honor students will have to memorize some of these formulas, but they're pretty simple to memorize. Everybody else, General Chem will get a reference sheet with all of them, so you don't have to memorize them. But what you will have to do is write them every single time we do a conversion. So what now? I'm going to go to the notes themselves and scroll down to the temperature conversions. Here we are. And we're going to go ahead and do some conversions. Okay, the first one is convert 32.50 degrees Celsius to kelvins. So I'm going to kelvins. So here's the formula, I'm going to use them. Kelvins. So I write it. Kelvins would equal the amount of Celsius, the degree Celsius, plus 273.15. So my degree Celsius is 32.50, and I add 273.15. And then I'm going to pull up my calculator. There it is. Just scooch it over, turn it on, and I'm going to be using this in a lot of the videos. Now these are pretty easy right now, but you will be able to see me use it in other videos where there's a little bit more to it. So it's 32.50 plus 273.15. Enter. Okay, 305.65. 305.65. 0.0565 kelvins. Notice it says kelvins. Now, I want you to follow this procedure. In order to get full credit, in order to understand and learn, because I don't make you memorize, you must write the formula like this with nothing, no numbers in it. Then you do the calculation part. You put in the numbers for me to see that you're putting it in the right spots, and you circle your final answer. Now, because we have not learned yet about sig figs, I'm not counting significant figure errors yet. So if you give me something that's close or one of the options, you're good. This is the answer for the first one. Now let's check the second one. Convert kelvins to Celsius. All right, so now Celsius is my final value, so I'm going to use this one because kelvins is involved. I'm going to write the formula first. That's the first step in doing the question. Minus 273.15. And then I'm going to put right in my actual values. I have 671.50 kelvins minus 273.15, and that's going to give me to my Celsius temperature. Pull my calculator back up and do this. 671.50 minus 273.15, enter. 398.35. 398.35 degrees Celsius. That's my final answer, so I circle my final answer. Notice again, I wrote the formula. This is part of doing the work. If you don't do this work, writing the formula, you lose a point. I write in the values to make sure they're in the right spots. You can't see that decimal point too well. Then I circle my final answer. This helps communicate to me that you know what you're doing. Now we're going to convert degrees Fahrenheit to kelvins. And there is no formula that goes straight from Fahrenheit to kelvins. But I can go from Fahrenheit, see Fahrenheit, to Celsius. So this is going to be a two-step conversion. So first I'm going to figure out what Celsius would be. And it's Fahrenheit minus 32 divided by 1.8. You must follow PEMDAS. Super important. PEMDAS. Order of operations. What is PEMDAS? Say it with me. Parentheses, exponents, multiplication, division, addition, subtraction. Or please excuse my dear Aunt Sally. This is the order of operations you must follow. So parentheses you do first. So inside parentheses is my Fahrenheit. So let me write in the numbers for the next step of this process. So my Fahrenheit is 46.54 minus 32 divided by 1.8. Okay, follow PEMDAS. First we do the parentheses. So 46.54 minus 32. Okay, 46.54 minus 32. So that's 14.54. Okay, 14.54 divided by 1.8. Okay, now I can do the next step in this process. 14.54 divided by 1.8. I get 8.07777 forever. 8. So 8.0777. I'm going to put an 8. Okay, I'm going to round it just a little bit. 8.078 or 8.08 or 8.1. All of these would be okay for this particular problem. This is degrees Celsius. Okay? Degrees Celsius. I'm going to use 8.1 degrees Celsius. That's the first part. Now, have I answered the question yet? Kelvins. I haven't got to kelvins yet. So now I'm going to convert Celsius to kelvins. So write the second formula. Kelvin equals degrees Celsius plus 273.15. 8.1 Celsius plus 273.15, and that's going to give me my final answer. 8.1 plus 273.15, 281.25. Okay? Whoops. 281.25 kelvins. Final answer. So this case, I needed two formulas. I used this formula and I use this formula. Those would all be a point. So that'd be a point for this formula, a point for this formula, and a point for the final answer. and a point for the middle answer as well. So this could be a 4-point question if I wanted it to be. All right, so be very careful. Now I want you to pause the video and convert 238.23 kelvins to Celsius and then convert it to Fahrenheit. Okay, and once you do that, then restart the video. All right, I'm going to assume that you did it. So let me put the answer up for you. Okay, so I did part of it for you, and I just wanted to talk about a few things. Notice I used the formula. I put it into the formula, and this time I ended up with a negative 34.92. That's important. And then I used the next formula to convert Celsius to Fahrenheit. Up here we converted Fahrenheit to Celsius. Now I want Celsius to Fahrenheit. Fahrenheit has to be the answer. I have to still follow PEMDAS. Please excuse my dear Aunt Sally. So parentheses first. So 1.8 times the negative 34.92 plus 32. And then we're going to get our final answer. So first PEMDAS, clear that out. 1.8 times negative 34. I wonder how I can do that on this. Oh, I know how to do backspace. So I have to go down here and hit this little negative parenthesis sign, negative 34.92. Enter. So that's a negative 62.856. And then I'm going to add 32. You got to make sure you do it in the right order. So negative 30.856. Negative 30.856 degrees Fahrenheit. I would take that because we're not doing significant figures yet, or I would take anything close to that at this point. Negative 30.86 or negative 30.9 degrees Fahrenheit. Final answer. So be very careful following the order of operations when you're doing these things. That's going to bring us to 2C, and that's going to be covered in the next video. So I'll see you soon.